So welcome to this last session of today. We have 3 papers in this session before we have the keynote in the afternoon. My name is Mikael Skov. I'm from Aalborg University in Denmark, and I'll be chairing this session. We have 3 papers on different aspects of tangibility. And the first paper is from people in Aarhus, will be presented by Emil Grønbæk, and it's called KirigamiTable, Designing for Proxemic Transitions with a Shape-Changing Tabletop. And before I give the word to Emil, I will just say that you can ask after the talk, which will be 10 minutes, you can ask questions in the chat, and then I will pick a number of people who can ask questions directly. So I will you can unmute yourself when I call your name, and then you can ask the question. So let's start. Emil, the stage is yours.
Thank you. So I'm gonna play this video here first.
Hi, I'm Emil Grønbæk from Aarhus University in Denmark. This research is done in collaboration with co-authors from Aarhus, Majken, Kim and Marianne, and is supported by Microsoft Research and the KB Lab. The talk is about KirigamiTable, a shape-changing interactive tabletop designed to support transitions between individual and teamwork. The core motivation of this research is designing for transitions in collaborative work. In a previous paper, we coined the term proxemic transitions to articulate the dynamic interplay between people, computers, and physical environments. In a field study, we found that during transitions, people often adapt to the environment for co-located collaboration. Imagine if we could instead physically reconfigure the computing environment. This is one of the great potentials of shape-changing interfaces at the scale of furniture. Researchers such as Takashima and colleagues and Ishii and colleagues have contributed prototype concepts of both shape-changing tabletops and wall displays. These are all focused on supporting transitions in collaborative work. But most of this prior research has focused on triggering shape changes and not so much on the actual interface transitions. In order to explore this gap, we developed KirigamiTable. With KirigamiTable, we make the following contributions. A novel user interface that supports collaboration around shape-changing tabletops, a set of interaction techniques that combine shape and content transformations, and demonstration of the principle of kirigami actuation for tabletops. I'll structure this talk by going through each of these contributions. First, let me show you a clip of the possible shape changes with KirigamiTable. Our first contribution is the design of the user interface for KirigamiTable. As you saw in the video, the table supports 3 configurations: flat-fold, 4-fold, and 2-fold. And the user interface is designed to exploit the qualities of these configurations for transitions in collaborative work. I'll first briefly explain how the prototype is implemented. For the display, we use dynamic projection mapping, where the current state from the actuators is used as input to adapt the graphics in real time. And an important disclaimer, all the interactions you will see are simulated via Wizard of Oz. I'll now talk about what we developed for the user interface. We see a great potential for KirigamiTable in supporting the social dynamics of creative work. To inform the interaction design, we developed an application scenario. The scenario is based on analysis of creative collaborative practices, and we found that they often involve transitions in the physical configuration of people. We have focused on one example, inspiration card workshops. It is a collaborative workshop format where technology experts and domain experts co-develop design concepts together. KirigamiTable is well suited for this use case. The workshop has a well-defined structure that takes participants through transitions between different physical configurations, working in sub-teams, individually, and as a whole team. I'll now play a video of the use case with KirigamiTable. So for shape-changing tabletops, it is not just the contents that are dynamic, but also the shape of the interface. And this requires that we completely rethink the interaction design. I'll now explain some of our interaction techniques, and these techniques are based on our work of addressing core challenges identified in prior work. And it is important to mention also that these are just a first exploration. So you should only regard them as design proposals. For this talk, I will focus on a few examples from the paper. First, I'll show how we have explored different ways of initiating transformations. We demonstrate two different approaches that both combine content and shape transformation. The Shape First widget has the three possible shape configurations as top menu items: flat fold, four-fold, and two-fold. And for each one, the user can then select between meaningful options for the content. The Content First widget supports the reverse interaction starting from the content items. A key difference in the two techniques is that the Shape First widget is permanently visible, whereas the Content First widget appears in context after a user has selected a group of items. Now, another important question is, what happens to display contents during and after shape transformations? I'll here focus on one example from our techniques that aim to address this question. What you've seen in the videos is that we propose to utilize shape changes for applying actions on the contents, such as subdividing, duplicating, or sharing items. But how can users anticipate shape changes to affect the content? We suggest a feed-forward mechanism inspired by Lindelbauer and colleagues, where we virtually alter the appearance of the Kirigami surface to preview how content will be reorganized. Specifically, we highlight edges on the surface folds and animate them to indicate zones for how contents are reorganized. You saw a glimpse of it earlier, but here it is in a bit more detail. Finally, I will talk about the principle of Kirigami actuation. The principle comes out of mechanical engineering research. Diaz and colleagues coined the term to refer to the design of mechanical actuators, where folding and cutting principles are used to generate different kinds of linear actuation, like rotations and lifts. So far, the experiments have been at the scale of paper sheets, so KirigamiTable is an experiment in scaling up the principle to furniture scale. We did several experiments on the table surface regarding size, dimensions, and different materials, as seen in the photos. And we are currently using a foam board, but want to build a more robust construction for the future. The undercarriage for the table construction has been built and generously provided by the Danish company Linak. It consists of 4 linear actuators, 2 vertical actuators for height shifting, and 2 horizontal actuators for deforming the kirigami surface. The 2 horizontal actuators expand in opposite direction, enabling a centralized surface deformation. This is a relatively simple construction if you compare to related systems. Often much more complex setups are needed for surface actuation. But in our approach, it is the kirigami patterns that do the heavy lifting. We use only simple linear actuation to achieve complex deformations. To conclude the talk, with KirigamiTable, we have contributed a novel interface for collaboration, a set of interaction techniques, and a demonstration of kirigami actuation for tabletops. Thanks for listening.
Thank you very much. Let's applaud Jens Emil for a good talk. And now the chat is open for questions. If you have questions for Jens Emil, please type them in the chat, or at least as a short question, then you can elaborate with sound. So I'll just allow a few seconds for people to type in questions.
I guess it explains itself.
I can start.
All right.
So thanks for a great talk and an interesting product. Could you talk a little bit about what do you have had any considerations about the scalability of such a product in terms of how many users can participate at the same time? So I can see from the different configurations that you allow up to, I don't know, 8 people in some of the configurations. But have you had any considerations on what are the scalability of such a system or product?
Yeah, great question. So I think that's actually an interesting challenge to explore further with, you know, these kirigami principles. Because as you can see, it's sort of that the current shape we're using is sort of pretty clearly also constrained in terms of the sort of physical affordances, you can say, in terms of like how many people can stand around it and things like that. But yeah, one of the reviewers were actually asking a similar question, and I guess like if you had like multiple of such kirigami patterns on the surface, you could maybe allow for more complex configurations of people and more people than that. So in the scenario that we played in the video, you see that it's sort of tailored to 4 people interacting together. And of course, one of the configurations supports a kind of like the one called twofold supports a kind of large vertical surface where, you know, an audience can appear as well and see from afar what happens on the screen. So yeah, I think that would be a challenge in terms of these patterns here.
Okay, I wasn't a reviewer. I have to say.
All right.
But there's still time for questions. So if you have questions, please write them in the chat. But let me just follow up on that. So have you thought? So this of course enables collocated collaboration, and this of course in itself limits the number of people that can participate, as you just briefly mentioned. Do you have any idea, or have you considered, is there anything that such a table would support more virtual collaboration, like having two teams at two tables collaborating on something virtually over distance. Has that been a consideration that you've had, or could you elaborate on that?
Right, yeah, so we haven't discussed remote collaboration so much, but I think, so I did a talk yesterday where a similar question came up, because so in my work I've been focusing on, co-located collaboration, but I think it's clear that some of these ideas of opening up to a more kind of physically dynamic interface is also very interesting in remote configurations, and particularly something that is emerging as a concept called hybrid meetings, where you have several co-located people also joining in a remote meetings setup like this. At the moment, we're one person at each endpoint, but just if you have two, the dynamics sort of completely change in terms of control of the endpoint, and how do we make sure that several people are within the field of view and so on. So I think having an interface that allows for sort of adapting the shape around which people can organize would be very valuable in the future, where we will start to see more kind of hybrid kinds of collaboration. I hope that answers the question.
It does. I was mostly curious about whether that had been a consideration or a next step or whatever. Let me.
It might be a next step now that we're in these times of social distancing.
Exactly. You need to build a bigger table for the 2 meters to be
right.
effectively. Let me just have a fun. Oh, there is one question. So that's from Anna Cantosalo. Could you state your unmute yourself and ask the question?
Yes, hello. I'm Anna Cantosalo from Aalto University. And I was wondering, since in your presentation you focus on pictorial media, does the KirigamiTable support other sorts of media, for example, the addition of text, or how do you suspect the addition of additional media would change how the table works?
Thanks for the question. So the answer is a bit mundane. Is the fact that we are using projection mapping for the setup. Currently, text doesn't look very well in terms of sort of conveying the power of this kind of interface. But if one of the next steps in terms of implementation on this kind of device would also be some LCD panels or something where you can get a more sort of high resolution on the surface, and then of course text and other kinds of UI become a lot more interesting. But the answer to your question is that it was really just sort of a concern of what sort of displays best and what is sort of simple in terms of conveying a rather complex kind of user interface where the shape and the contents are dynamic together. So it had to be these sort of self-contained entities that you could see how they would move around and cluster in different ways. And this inspiration card workshop scenario that we worked with also supported that kind of quality. So
okay. Thank you very much. Time is almost up. Let's thank Jens Emil Grønbæk once again for a great talk and discussion. So the next paper and presentation that is up is called BodyLights, Open-Ended Augmented Feedback to Support Trainings Towards a Correct Exercise Execution, and will be presented by Laia Turmo Vidal from Uppsala University. So Laia, you are welcome to share your slides.
Do you see
start your presentation?
Do you see the slides?
Yes.
Good. Good. Then I'm going to start it straight away.
Thanks.
Hello, my name is Laia Turmo Vidal, and I'm presenting the work that we did with Hugh Zhu and Abraham Riego-Delgado on BodyLights, open-ended augmented feedback to support training towards a correct exercise execution. Most movement teaching and learning practices, like sports or fitness training, require a correct movement execution to make training effective and not harmful. The apparition of body sensing technologies has led to a plethora of designs that focus on supporting trainees in achieving a correct movement technique. But the current overarching design approach in these solutions focuses on automatizing correction and instruction processes, giving technology the assessing role. These solutions often present technical limitations in assessing movement execution, providing feedback on singled-out technique parameters, for instance balance, or course indicators that disregard precision and accuracy. And they usually are able to provide feedback only for a limited set of exercises, 1 or 2. In addition, the assumption behind this design approach is that what constitutes a correct technique can be specified and modeled under simplifying benchmarks. But in reality, what entails a correct technique is contextual and situated, depending on individual trainees, their skills, and their abilities. In this paper, we explored a complementary design approach in which technology offers open-ended augmented feedback. These are open representations of body data, presented to users in a non-assessing and non-interpretative way. Previous works designing for physical training have proven that open-ended feedback is useful to support a general reflection on performance or instructions. So we wondered if this approach would also be useful to support a very normative practice, and if this type of feedback could help training towards a correct exercise execution. To explore this question, we turned to strength training as a practice, and engaged in a research through design project following an activity, soma-based and practice-based design approach. We involved a personal trainer and expert trainees in the co-creation and made use of embodied design methods. We designed and studied the inclusion of BodyLights in 18 strength training exercises. Design. BodyLights is a 3D printed wearable optomechanical device. It is inspired by previous works using visualizations to support physical training. BodyLights is placed in key body parts or in the equipment, as you can see in the pictures, and projects a laser cross in the environment that moves as the wearer moves. We designed the inclusion of BodyLights in 18 different strength training exercises. We did so together with a certified personal trainer and 3 experienced trainees over the course of 4 co-design workshops of around 3 hours each. We focused on key movement technique aspects and common errors that BodyLights could visualize for each exercise. Our design considerations for each exercise were the course location of BodyLights in the body or in the equipment, the projection direction, and the interplay of the projection with environment and spatial marks. The personal trainer would use a dynamic interplay between the BodyLights projection and these spatial references to provide instructions and feedback. The final set of exercises included 7 full-body exercises consisting of planks and 5 variations of planks and deadlifts, 4 lower body exercises including squats, leg bridges, and lunges, 4 upper body exercises including dumbbell raises and press, barbell press, and barbell row, and 2 core exercises, crunches and Swiss ball abs. This is an example of how our design works. This is a simple plank, where a key technique aspect is to have a proper back posture, with the knees, the hips, and the shoulders aligned in a straight line, as you can see in the first picture. The personal trainer positions BodyLights in the trainee's chest and adjusts them so that when the trainee is in the correct position, the cross projection is placed across their palms in between their hands, as you can also see in the first picture. If the trainee during the exercise deviates from the correct posture by bending or extending the back, as in the other 2 pictures, the projection will move from in between the hands, either further in the mat or back in the mat or to one side or another. This is something that the trainee can see, but that the personal trainer can also use to give further cues or corrections or feedback. Study. We ran an evaluation study with 15 participants, 7 women and 8 men. 7 of them were beginners, 5 intermediate, and 3 advanced. Our study consisted of participating 3 times over 2 weeks in a tailored and balanced workout, consisting of 4 to 6 of our exercises and lasting 40 minutes approximately. We recorded a training session and the post-work interviews with the trainees and the personal trainer, and did a video analysis and thematic analysis on the data. Results. Our results show that both the personal trainer and the trainees found the inclusion of BodyLights useful to support execution, error identification, and to provide tailored instructions and feedback. It helped in execution because trainees were able to visualize different technique parameters at the same time, such as movement trajectory. For instance, here, doing a Swiss ball ups, the projected cross travels up the wall as the trainee goes back, tracing a straight line. Another one is posture, as in the planks, the example that I presented before. The third one is movement pace. For instance, while doing squats, several trainees became aware of how their pace going down was faster than going up because they could see it now visualized in the projections of BodyLights. The trainees used this pace visualization to pace their movement, and the personal trainer to give them cues about speed. And finally, BodyLights could also visualize muscle engagement. For instance, in this barbell bend row, if trainees engage too much their upper back muscles when rowing, instead of the arms, the projection of the BodyLights that they have in the chest will significantly move away from the marker in the floor, as you can see in the second picture. BodyLights supported error identification because they offered a precise visualization of all those parameters. As one trainee mentioned, "For me, it's like a mirror. It's a way in which I can see my body. It's reflecting my movements, how tired I am, how straight I am, how fast I move." Trainees could compare their visualization to the benchmark given by the personal trainer, which they used to identify errors. As the personal trainer mentioned, "I don't need to repeat the instruction every time. I just confide in BodyLights to take care of it. I don't need to repeat the basics. With the light, they know, and some can correct it by themselves." BodyLights also supported the personal trainer in providing tailored instructions and feedback. The personal trainer could adapt the design to suit different trainees, for instance by repositioning BodyLights in their body, adjusting the projection angle, and tailoring spatial references. Also, the personal trainer could use the visualizations to adapt the instructions and feedback, for instance to draw attention to different parameters for different trainees at different skill levels, or adjust what the correct technique was for each individual. You can read more details about the results in the paper, but I want to end this presentation discussing some key design takeaways and the contribution of our work. In the paper, we present 4 key design takeaways that underpin the usefulness of BodyLights. Again, I refer you to the paper for a more detailed and nuanced discussion on them. First, intimate correspondence. The augmented feedback was perceived as an extension of the body, and trainees could easily relate to it and understand it. Second, the fact that BodyLights augmented several important technique parameters at the same time. Third, that it offered a shared frame of reference between the personal trainer and the trainees, allowing both of them to refer and orient to the visualizations and use those to communicate with each other. Finally, that it offered trainees with an external focus of attention and feedback, which in sports science has been widely acknowledged to support working towards a correct technique. In terms of contribution, beyond the usefulness of training with BodyLights, in the paper we discuss what an open-ended feedback offered in comparison to prevailing design approaches to support training towards a correct exercise execution. First, it offered versatility in the parameters augmented, given that BodyLights do not sense nor recognize parameters per se, but rather offer a visualization that the personal trainer endows with meaning. Second, versatility in exercise is supported, from 1 or 2 that are commonly supported to 18 in our design. And finally, adaptability to individual trainees at different skill levels, catering to their anatomical particularities, their needs, and their abilities. Our work extends current work on technology design for strength training, and more generally, we hope it might inspire future design work for movement teaching and learning domains, where correctness of execution is crucial. And with this, I finish my presentation. I encourage you all to read the paper for more nuanced details on the project, on the insights, and the design takeaways. But thank you very much for being here today. And also special thanks to Annika Vern and Dimitris Babalikis for their comments and their help. I will actually be taking questions now over Zoom. Thanks.
Thank you. Let's applaud Laia. So questions for Laia's talk and paper, you're welcome to put them in the chat. I'll give you a few seconds to do that, and then I'll pick some or I'll ask some myself. So should we start? There's one from the first one is from Dag Svanes. Could you state your question, Dag?
Yeah. Do you hear me?
Yes.
Good, thank you. Yeah, very interesting talk. I really liked it. It's sort of,
Thanks.
it's aligning with a lot of work we do in Trondheim with a different approach, of course, but with the aim to do correct movements. And what I really it made me think, I mean, the very nice thing about it is that it's low tech. I mean, there's no computer in there, and that's good. So one question, my first question is towards this thing with first person, third person, because the moment you do this kind of externalization of your movements, it's kind of similar to in a mirror, because some physiotherapists, for example, they say that we shouldn't have mirrors because mirrors make people not feel in their body that they do the right movement. So have you sort of reflected on to what extent this, when you take it away, will they still know what is the right movement? Because that requires that you feel it.
Yeah, thanks for your question. Actually, I want to mention two things about that. The first one is that we were actually looking as well on how people use mirrors, because in strength training, mirrors are something that people use a lot. And I think that one difference here is that by using mirrors, it really puts you in weird positions because it's not something that you always have in front of your eyes. So that's one of the design considerations we had, how they could see this feedback in a way that didn't put like body constraints or weird postures. That on one side. And on the other side, it's something that I'm interested in checking, like how the use of technology or the usefulness that they find changes over time. It's not the type of study that we run, but I can say that we train with each trainee 3 times, and especially the more advanced ones, in the third session, they could already say, like, I think I would not need the lights anymore because I remember what the lights should be doing. So I can the lights help them kind of reach what they were previously doing with the lights to what they should be doing now. So they could see how their usefulness of the lights were kind of diminishing with time. But I also have to say that was more with more advanced trainees, with more beginner trainees, they were still relying a lot on the lights. So that's a quite interesting question. Like what happens if you actually train, if you use that as a training method, right? Do they become too dependent on the lights? Does it become, as I would like, a training tool or a training aid until they develop their own skills? I don't have a clear answer yet.
Yeah, interesting. Okay, thank you very much.
Thank you very much.
Okay, we have a few more questions. So there's one from Paulina Bajkowska.
Yeah, I was just thinking, what other forms of training could this be applicable to, and why specifically strength training? Was there something particular about that choice, or?
It's as I said, like this is based on previous work that we've done in our group, and we've been working. I personally been working with this design for a long time, so with different design, different levels of the technology. And we've tried this in circus training as well. We've tried this in yoga. And my reason to go to strength training was exactly that, because we've seen that it works quite well in more in practices where maybe being correct is not so important, but I always had the hunch that it could help as well in very precise practices where you really need to move in very specific ways, very, very determined ways. So strength training was actually just one example of a very normative practice that requires a very strict way of doing things so you don't injure yourself. There was nothing else behind that, apart that I myself train strength training and I like it.
Thank you.
Okay, and we have one final questions from Clayman Lilia. Clayman?
Hi. Very interesting idea and study. Well, my question is a bit similar to the first one. So I was wondering, once you remove this augmented feedback, if you noticed any troubles with participants executing the exercises, and have you considered to not have that feedback all the time there?
Yeah, so on the final session, we removed the feedback, and I have to say there were some interesting things happening there. I have some of it on the paper, but it's not the main thing. What happened is that it provided such a clear visualization of their body that some people find it stressful, especially people that were very advanced. They were saying, I realize now that I'm not doing things as right as I thought I was doing them, and they were not feeling very comfortable with that. So when we removed the lights, their feedback was like, I feel more relaxed, or I feel like less stressed because I don't have this constant reminder of how I'm doing things. But then assessing it with a personal trainer without the lights in those repetitions, we could see how they actually were doing things worse, in a worse way. So there's a bit the balance that I have not studied in this study, but there is a bit the balance of how they felt, or if it was creating for some of them some stress because they could see that they were doing things wrongly, but at the same time, when you remove it, their performance was worse. So how do you balance like the two of them? This is not a question that we explored much, because just some participants had this idea. And as I said, for others, it actually, they were saying like, okay, now I can remember how I was doing this exercise with light. So if you remove it, I just have in my mind how it was moving before. So it actually has helped me get to that point. So yeah, I think that based on your question and on Doug's questions before, there is definitely need for a more long-term study of how actually the practice change, or how their skills change through training with it in a more like in a longitudinal study.
Thank you.
Thanks.
Okay, let me just have a final question for you before time's up. So this is not my area of expertise, but I assume could you elaborate a little bit upon what are the aspects of precision in body posture and the way that you perform these exercises? I assume that there are first some individual differences between people on when you are in a perfect position for a particular kind of exercise, and also how do you map that in your system? So do you calibrate that somehow, or?
So let me reply with an example, a squat, that I think that everyone knows more or less like what a squat is. If you check YouTube videos, or if you check like guides on how to do a squat, there are like 1 or 2 ways, different forms of doing a squat. But our assumption, what happens is that actually how you can do a squat depends a lot on exactly that, your skill levels, even anatomical things like how long your legs are, and how flexible you are. And in order to do a squat in a way that you don't injure yourself, especially if you work with weights, you have to take all these things into consideration. And then there's all these parameters. It's not only posture, it's as well the movement pace, is how the different body parts are aligned to each other. And then when you work with a personal trainer, usually the personal trainer is able to assess like both your anatomical capabilities, your skill level, and provide more tailored feedback, more than just like this, the typical way of squat. So the way that we work with it, I insist, is that BodyLights were not providing any assessment on whereas this is a good way of doing the squat or not. It was just visualizing some of these parameters. And then the personal trainer was tailoring for each person not only where to wear BodyLights and how to project, etc., but also the type of feedback that they were giving. So, for instance, in the squats, we could see that for more beginner participants, they were correcting a lot of the posture. You could see, for instance, you had 2 lights like this, and if they were not aligned, you could see one side higher than the other. For more advanced participants that they are quite already knowledgeable on how to do this, she was turning into more nuanced parameters like the speed of the execution. So since it visualized so many parameters in so many open ways, the personal trainer could actually cherry pick what aspects to bring the trainees' attentions to. I don't know if that replies a bit your question.
Oh, it does. Yes. Thank you very much.
Thank you.
Let's thank Laia once again for an interesting talk.
Thanks.
All right, we have 1 paper left in this session, which will be presented by Niels Christian Nilsson. It's called Knock on Wood, Combining Redirected Touching and Physical Props for Tool-Based Interaction in Virtual Reality. Niels, you're welcome to bring up your slides or your video.
Can you see the slides?
Yes.
Good. Okay. Yeah. Well, since we had some issues with the video, I'll just do it live. So yeah, my name is Niels. I'm from Aalborg University, and I'll present our paper, Knock on Wood, combining redirected touching and physical props for tool-based interaction in virtual reality. But so before I say anything else, I really want to acknowledge the efforts of Patrick and Oana, the two of our former master students, and they were really the ones that did all the hard work and turned this idea into a working prototype and actually ran the user study. So with that said, so while current virtual reality systems offer compelling audiovisual experiences, the sense of touch still presents a significant barrier to complete immersion in virtual reality. And of course, there exists a lot of solutions to this problem out there, but I'll focus on one in particular, namely using physical props to provide touch in VR. And physical props can serve as proxies for virtual objects, and they offer a convenient and inexpensive approach to virtual touch. So despite these advantages, it's by no means trivial to rely on physical props as a source of haptic feedback in VR. And especially if you have users, if your users are offered a high degree of freedom to interact within sort of more complex virtual environments. One of the things we write about in this paper is that we argue that there exists at least 3 criteria for successfully deploying physical props in virtual reality. And I want to very briefly outline the 3 for you and provide one example of previous work that has addressed these criteria. So the first criteria we call sufficient similarity. And the idea here is that all physical props that you use as proxies, they should be sufficiently similar to the virtual objects they serve as proxies for. So that is that the real and the virtual objects should resemble each other with respect to haptic properties such as weight, shape, size, and texture, for example. And this is, of course, somewhat impractical if you have a VR application that allows the user to interact with many different objects, because you would need objects that vary in terms of these haptic properties. And yeah, so just to show you one example of how this criterion has been addressed in the past, what you're seeing here in the video is an example of redirected touching. So here the idea is that we distort the mapping between the user's real and virtual hand movements, and that allows us to map somewhat oddly shaped virtual objects to the square box, as you see here. So again, relying on visual dominance. The second criteria we dubbed complete co-location, and here the idea is that all virtual objects that the user may want to interact with should be represented by a physical prop. So the idea is that the user should never reach for an object in the virtual environment and not encounter a physical prop. And this, of course, limits the utility of physical props in the sense that you need a large number or it decreases the utility as the complexity of the virtual environment increases, so to speak. So for that reason, it would be very valuable to have some approaches that allow you to repurpose the same physical prop so it can serve as a proxy for many virtual objects. And one way of doing that is through so-called haptic retargeting. And you see sort of the original work in this video. The idea is with haptic retargeting, it's similar to redirected touching, but not quite the same. But the idea is that you warp either the virtual environment, the user's body, or both. And in that way, you can map multiple virtual objects onto a single physical prop. The third and final criterion is what we call compelling contact forces. And here the idea is that if the user touches an object or is grasping an object that is influenced by contact forces originating inside the virtual environment, then appropriate information about these forces should be transmitted to the user through the grasped object. So for example, if the object you're holding in your hand is colliding with a virtual object or scraping against a virtual surface, for example, then we need these forces sort of transmitted through the object. And just to provide one example, a fun one here, mutual human actuation. The idea is that you have 2 users, each of them are holding a prop. The 2 props are connected. And in that way, the 2 users actually provide each other haptic feedback. And in that way, so that addresses this third criterion. And that brings me to the work described in our paper. So we propose redirected tool-mediated manipulation, or just RTMM for short. And the idea here is that we use visual dominance to address the criteria of compelling contact forces during tool-based manipulation in VR. And to briefly explain the idea, when the user is grasping a physical prop that serves as a proxy for a virtual tool, then we introduce a second physical prop So in this case, the table you see there. And that serves as a proxy for the object being manipulated. So, and it provides passive haptic feedback when the two props collide or come into contact. And then we use something similar to redirected touching in order to change the user's perception of the interaction. So for example, we have attempted to create the sensation of changing the shape or the position of a virtual object. So that's the core idea. We implemented 3 prototypes that relies on this technique. So one based on a hammer or interaction using a hammer, one using interaction based on a screwdriver, and finally virtual sawing. And I'll give you a quick preview of how it looks, but you'll have to refer to the paper for the details about the algorithms. So here you see an example of virtual hammering. So the idea is essentially that we manipulate the mapping between the physical and the virtual hammer's vertical position, and this ensures that the physical hammer always strikes the physical surface whenever the virtual hammer hits the virtual nail. And here you see an example of redirected screwing. So the idea is it's a similar kind of manipulation. We manipulate the mapping of the vertical movements, and in that way we ensure that the screwdriver is always in contact with the table whenever the user is in contact with the virtual screw. And finally, redirected sawing. So here we use 2 types of manipulation. We visually offset the virtual saw in 2 dimensions to on the one hand, give the impression that you're cutting through the plank, but we also offset the position along the plank. And this and because the user corrects for this offset, we can ensure that when the user cuts through the virtual plank, then their hand also slips off of the edge of the physical plank. And in that sense, you get the impression of having cut through the plank, so to speak. Good. And that brings me to the evaluation we performed. So to evaluate the developed prototypes, we performed a within-subject study with 20 participants, and we compared 3 conditions in terms of realism, preference, and precision. The 3 conditions we compared was 1, just interaction using a regular controller. So you would either hammer, saw, or screw using a regular controller. Then we had another condition where the participants just used a single physical prop. So again, the same tools, either a hammer, a screwdriver, or a saw. And finally, we had a condition where we combined a tool and a surface, and then we used a redirected tool-mediated manipulation to make the interaction possible. And very briefly, the procedure. So we had 3 tools and 3 conditions. So that gives us a total of 9 trials per participant. The conditions were presented in blocks of 3. So you tried the hammer in one block, the screwdriver in one block, and the saw in one block, so to speak, and tried the three different versions of that using the different interaction methods for easier comparison. And of course, the blocks were randomized the order, and so was the order of the conditions within each block. In the beginning of each block, the participants were asked to perform a reference task. So they would actually be asked to cut a board, hammer a real nail, or screw a screw, drive a screw into a board. And this was sort of meant to serve as a reference when they were subsequently asked to evaluate how realistic the different conditions were. After exposure to each condition, we administered a short questionnaire. So it just had 4 questionnaire items, all answered on 7-point rating scales. And we basically asked about perceived realism and perceptual similarities. So how similar was the experience to what they had just tried during the reference task? And high ratings indicated high realism or high similarity. And during each condition, we also logged data related to the participants' movement, or rather the movement of the tools, in order to get an impression of how precise they were when performing the task. So for example, for the hammer, we looked at how far away from the nail the hammer was during each strike. And to very, very briefly summarize the findings. So the questionnaire data and the preference ratings all indicated that redirected tool-mediated manipulation was perceived as the most realistic, and it resembled the real thing the most. So that was sort of a general trend. And it was also interesting to note that there seemed to be a correspondence between what people found the most realistic and what they preferred, with the exception of a few participants who actually preferred just using the controller because it was a lot easier, so to speak, and less fatiguing. We also found that there was a difference between the three tools. So, and we do think that that has something to do with how they were implemented. But basically, the hammer seemed to work the best. The participants found that to be the most realistic, and the screwdriver was the least realistic. In terms of precision, we found some interesting but a little bit surprising results. I think we expected that because we are manipulating the mapping between physical and virtual movements, that this would impair precision, but we didn't find any sort of significant impairments on precision in terms of either of the three tools. With that said, we could see that it does seem like participants found it slightly harder to cut along a predefined line when we were actually manipulating the movement of the saw, but we would need to run further studies to determine if that was actually the case. Good, so just to quickly conclude, so in this paper, we introduced the concept of redirected tool-mediated manipulation that combines two or more physical props and redirected touching. We presented 3 prototypes of this approach, and finally, we presented the results of a user study evaluating the perceived realism and precision of 3 prototypes by comparing them to interaction using a single physical prop and a standard VR controller. Thank you for listening, and I'm happy to take some questions now.
Thank you. So again, thank you for an interesting talk, Niels Christian. Questions can be put forward in the chat, and I'll wait a few seconds before I'll go on. So please state your questions. Let me start, and then there might be others who will. So could you elaborate a little bit upon? So when I saw those small video clips of people with the hammers and the sawing, could you elaborate a little bit upon safety and safety concerns, or did you anticipate anything or experience anything? That's one thing. So how was safety handled? And related to that, are there any limitations to this approach in terms of what kind of tools or crafts you can actually support?
Yeah. So on the safety point, so I didn't mention that explicitly, but the saw, maybe it wasn't visible from the video, but there was actually the protective guard on. So you couldn't cut yourself. Of course, we were sort of fairly cautious when performing the study. One thing that's worth noting is that ideally we would have liked to not inform the participants of whether there was a second prop present or not, but we felt that we were forced to do that simply because otherwise they might strike, or if they started out by experiencing the table and thought that there was they would meet some resistance, then in the next condition, if they were just holding a hammer, they might start striking themselves. So I think you definitely have to be a little bit cautious. I think particularly also for the saw when you slip off of the edge, that one I think would need a bit more work in order to be useful sort of in a safe manner. No doubt about that. And yes, oh yeah, your second point was about the sort of the generalizability of the techniques, basically, or the constraints of them. Yeah. Yes. So I think so. This work was primarily meant more as sort of a proof of concept to show that these manipulations also work when we apply them to tools. I do think that they could be used in a wide variety of different contexts. I didn't mention that in the talk, but we quite deliberately chose tasks and tools that involve different types of manipulation. So we had the hammer is a discrete impact. Mm-hmm. We have the screwdriver, which is sort of continuously manipulating something, and then the saw is also continuous, but here you change the geometry of an object. And I do think that they could probably be used for a wide variety of different tasks that involve these types of manipulation. With that said, So I started out by talking about these 3 criteria that we need to complete co-location, for example. And even though these techniques work fairly well in this constraint scenario, of course, if you want to simulate a full construction site, you're going to run into the exact same problems as you would when using any other props, because you would need to have secondary proxies all around in order to accommodate this kind of interaction.
Yeah. So that wasn't visible from the video, the first one on safety. Did any of the subjects articulate any concerns or came with suggestions on to address this issue? I would assume if I were a participant, I would be a little.
Yeah. Well, actually, what we observed was, so we think that one of the, as I mentioned during the talk, we did not find major differences in terms of precision. And one of the things we observed, and we collected qualitative feedback as well. And we noted that some participants appeared, or quite a few participants appeared to behave much more cautiously when they were given the physical tool. Mm-hmm. And they also themselves expressed that once they realized that there was actually a table they could hammer on, they started being much more cautious because they were worried about both breaking the whatever, because they didn't know what surface they were touching. And generally, it took a little while from they were first given the tool and had explored the interaction a little bit before they sort of felt more free to hammer properly or saw properly as well. But also one thing that we have not explored, but I think it would be worth exploring, is that we don't know to what extent does the mass of an object and just the shape matter in terms of realism, for example. So it's entirely possible that you could use prop. Now we use the actual tools, but you could create props that are lighter, that are softer, but the shape is the same. Maybe the weight is the same, but they're not hard in the tip, for example. So in that sense, you could resolve some of these issues. And I do think that would sort of be the way going forward.
Yes. All right. We have a question from Sophie Landwehr.
Thank you, Niels, for your talk. I was wondering about the applicability of this. Like, would you see there's any like certain cases where this would be like good to use? For example, I was relating to DIY videos and how-to videos and kind of like thoughts around expertise or like kind of learning something.
Yeah. I mean, we note that in the paper as well, and that's of course the big question. And that so in the VR community, there's sort of a long history of applying these types of manipulations, and we know relatively little about how that affects skill transfer, for example. So of course, we envision that maybe this could be used for a training scenario, but again, introducing a visual and proprioceptive mismatch, I'm not sure that's a good idea in terms of training. And it's actually one of the things that we would very much like to explore is prolonged usage of these kind of scenarios. What would that do? So for now, we're a little bit cautious and just say it makes the experience more realistic. And it is a lot of fun having the physical props, but I'm not sure I would recommend using it in a learning scenario just yet. We'll have to get some data on that.
Okay. Let's once again thanks Niels Christian for a great talk. And this concludes this interesting session on tangibility. I assume that the keynote will take place soon at 12 o'clock in, I think it's in track 1. So we will all have to change tracks to go in and watch that keynote. Thank you very much for attending this track. Thank you.